In this video, we're going to introduce the concept of potential energy as an energy related to the configuration or position in the system. And we're going to start seeing how we can use these energy quantities to describe a system in total. We'll go back to that diagram that we had in a previous video where I have these different kinds of energy. We see K represents kinetic energy, the energy of motion that we've defined previously. PE represents potential energy. We have chemical energy. We have thermal energy relating to temperature. And these arrows represent ways that these energies can sort of transform from one kind to another. We'll see many instances where we can transform from kinetic energy to potential energy and back again. We can have chemical energy transforming to either potential or kinetic energy depending on our system. We'll see that these arrows for thermal energy are one-way arrows. We'll talk about that more actually later in the semester, why that one-way direction is important. But I want to draw our attention to is that a system can be described as having a total energy. It says here that the energy is the property of a system. I have the kinetic plus the potential plus the thermal plus the chemical plus however many energies I have. I can talk about the total energy in my system. Within my system, I can transform that energy from one type to another without a loss. That's one of the definitions of my system, is that nothing else is acting on it, just things acting within it. Some energy transformations, if we want to think about what this might look like, well, maybe we eat some food and get chemical energy, and then we break those those bonds up in our food, and we get the energy from breaking those molecules apart. And then our body transforms that into energy that we can use our muscles to lift this barbell up and give it gravitational potential energy. So this only gained gravitational potential energy because we ate food to lift it up. We can have someone sliding into second base, so that energy of motion is going to change to thermal energy from the friction of them on the ground. Here's a very interesting example, something like will work in a coming problem later in class. We have these U's, that's just different notation from a previous textbook. Imagine that says PE spring and PE gravitational. So the diver jumps down on the board and flexes that board. That would be spring potential energy. Then that board bounces back. They start to move, so the system transforms into kinetic energy. But then as that diver jumps off the board, they go higher and higher and higher, so they get gravitational potential energy. So we have energy transforming from one kind to another, and we see depending on the particular object in the system, we have a different energy that we're talking about. Kinetic energy was 1/2 mv squared, so whenever we're moving we have kinetic energy. Gravitational potential energy is related to the elevation. Spring potential energy is related to that board flexing, or if I actually had a spring, it getting shorter or longer, as we'll see in future problems. So the law of the conservation of energy says that within an isolated system, that means nothing is acting on my system is contained within itself, the total energy remains constant. That means that my changes in energy in my system equals 0, right? The total energy remains constant. This says that it does not change. But note how I can have multiple parts: my kinetic energy, my potential energy, my elastic potential energy, my thermal energy. The total change in those is equal to 0. And as we work more and more complex problems, we'll see that there are times when my kinetic energy changes and my potential energy changes, but the total change of those summed together is going to be 0. That's what we mean by energy conservation. Let's start by defining potential energy first. Potential energy is an energy associated with a configuration of a system. If I look at a system and notice that it is spatially different, I've got energy associated with it. So let's just say that I've got object 1, object 2, and object 3, like this, right? And then at some later time, I happen upon my system, and it looks like this: object 1, object 2, and object 3. So this is time t1, this is sometime later t2. I know that if I had 1, 2, and 3 laid out like this, and later I see 1, 2, and 3, they've been moved around, the configuration is different. That did not happen spontaneously. Well, it might have happened spontaneously depending on the forces, but let's just say that didn't happen without something doing energy on those objects. Here was my configuration laid out, at a right angle. Now they're in a different spot. Something had to move these around by pushing on them, doing work on them, so we can actually quantify that something about the energy of this configuration is different than it was here. That's what we're really talking about potential energy, is my configuration of my system changing. Now, how does that change? Well, it might change by something moving higher, right? If something moves up in the Earth's gravitational field, we say that it has a greater gravitational potential energy. We could have a spring or something else that is stretchy, and we could change the spring potential energy. I've got more potential energy in a spring that is compressed than I have in a spring that is stretched out, because I have a different potential energy. There are forces at play on that spring, and those forces can act on other objects in my system. We define the gravitational potential energy as the mass times the gravitational acceleration times y, where y is the height above a defined 0 point. We only care about changes in potential, so that means we can declare 0 to be wherever we want. This idea of changes is important. We'll see as we solve problems, we always ask ourselves, what's the initial energy and what's the final energy? There's always a before and an after. That before and after, that change from before to after is what matters, so we can call either of them 0 as we see fit. Let's start by looking at a simple example where I have a ball thrown upward with an initial speed, and I want to know the maximum height that it reaches. Well, if our system is the ball and the Earth, then we can talk about the configuration between the ball and the Earth changing as that ball goes up. So here's my initial moment. I have my ball on the ground and is traveling up with an initial velocity, vi. And then at some time later in my final situation, I have my ball up here with Vf equals 0, and I have reached some height, let's call it h, right? Some height off the ground. Let's call the ground y equals 0. So I know that the total change in energy for my system is 0. That means that my energy final minus energy initial is equal to 0. So that's another way of saying that the energy final is equal to the energy initial. So let's work with that. Notice here I have kinetic energy. Here I have gravitational potential energy, but 0 kinetic energy. So if I look back at, I'm going to keep this picture in my brain, but I'm going to move over here to actually write a bit smaller, right? So we're saying that my energy final equals my energy initial, and I know that I've got kinetic energy and gravitational potential energy that I want to consider. So my kinetic energy final plus my gravitational potential energy final has got to equal my kinetic energy initial plus my gravitational potential energy initial. Well, my kinetic energy final was 0 because I'm at rest. My gravitational potential energy final is m times g times y final, or I called it height h, but that really doesn't matter. My kinetic energy initial is 1/2 m v initial squared. My initial gravitational potential energy is 0 because I'm starting at the ground, right? I'm saying that I start at height of 0, right? Y equals 0 over here as well. So this allows me to solve for y final. See, my masses cancel. So I get y final is equal to 1/2 times v initial squared over g. And that allows me to put in the values that I was given, because I actually was told that initial velocity is 4 meters per second squared over 9.8 meters per second squared, and that gives me a y final of 0.816 meters. Now, I could have solved this problem using kinematics. Note how this solution approach doesn't involve time at all. I would need to either find time or use an equation that used time if I wanted to use chapter 2 ideas to solve this. Energy is usually a lot more straightforward, especially when I don't care about time. I only care about what my system looks like initially, what my system looks like finally, and using the idea that energy is conserved, it allows me to calculate something of interest for my system. So in the future in class, we're going to work more and more complex problems, all of them starting with this idea that the total energy of my system does not change because I'm working on it, as we'll see as we work more and more complex problems.